like. I guess that's the most simple way to proceed. So we are going to start the last session of the workshop with Chris Hirata telling us about non-Gaussianity.
Oh, wait, so are you booking them or is it?
No. But the secretary at the entrance can help you to
And are those times when we want to be at the airport or
No,
to leave here?
I'm assuming it's the time to leave. It's not the time of the plane.
Is there a pointer?
Yeah, where's the... Right here.
But this one works. No?
That one does not work.
All right, good.
Hi, I'm Chris, and I'm going to talk about. I'm Chris, and I'm going to tell you about non-Gaussianity, primordial non-Gaussianity, and constraining it with large-scale structure measurements. The talk basically boils down to three parts. I'm going to begin with some boring theory, most of which I lifted from Neil's paper with some refinements. Then I'm going to tell you what our group, led by Andrzej Slosar and company, has done with this in the Sloan Digital Sky Survey. And finally, I'm going to talk about future prospects, which is where I give you all my random speculations and qualitative ideas of what can go right and wrong with this. So, first of all, there are many types of non-Gaussianity. The one I'm going to talk about is the most commonly considered type of non-Gaussianity, the so-called local type or FNL type, where the primordial potential is written in terms of this field phi, which is Gaussian, plus a nonlinear correction. So the idea is that this would arise, for example, if I had a field during inflation, perhaps a curvaton field, and the actual potential that I get out is some nonlinear function of what came out of inflation. There may be other ways to get this. There may be non-Gaussianities that don't look like this, but this is, at least for the moment, commonly used. And it's a benchmark for how well we can test whether the primordial fluctuations truly are Gaussian. Throughout this talk, and in I think most of the non-Gaussianity literature today, positive potential is in overdense regions. So potential is greatest down here, and is less up there. So it's backwards, and so you should just keep in mind if that confuses you that -1 equals 1. This type of remapping results in a skewed gravitational potential distribution. So as you can see, instead of being a pure Gaussian, a cartoon of which I drew here, I can get a distribution that is peaked and then has a long tail to either positive or negative potentials, or positive or negative densities, if I drew this in terms of densities. So which one I get depends on the sign of FNL. And just to normalize things for you, because phi is very small, the fractional non-Gaussianity is actually of order FNL times phi. So order unity non-Gaussianity in terms of the shape of this distribution would correspond to FNL equals 10 to the 4, or some ridiculous value like that. Now there are a few ways to go about doing this. The one that everyone knows about today because of the WMAP papers is to look at the microwave background. So this type of skewed distribution that I talked about will show up if you measure the skewness, or more generally the three-point function or bispectrum of the microwave background. You can construct various estimators for that. I'll say a little bit more about those results. You could do the same thing. In large-scale structure. The worry there, and the reason I think why this did not take off, even though the number of modes observed in large-scale structure was for a long time greater than those that were measured in the microwave background, is that large-scale structure, of course, has a large bispectrum from nonlinear evolution, whereas the CMB has density contrasts of 10 to the -5, so you might think that's a much smaller deal for the CMB. A third way to do it, which I'm not going to say anything about today, is the cluster mass function. Neil briefly touched on that during his talk. But if I have a skewed distribution like this, you could imagine that for very rare massive objects, the abundance of such things could be far greater than what you would get in the Gaussian case. This was popular 10 years ago, I think. I wasn't actually around then. I read about it in history books. And finally, the subject today is the ultra-large scale structure power spectrum. Basically, if one goes to very large scales, then because this distribution involves potentials rather than densities, there can actually be a very large contribution on large angular scales because the primordial potential fluctuations are close to scale invariant, even though the density perturbations go down towards 0 as you go to larger and larger scales. And there was an excellent paper last year by people here that showed how this gives rise to scale-dependent bias. So I said I would tell you about the CMB results. Here are some recent examples. The first two WMAP results have been superseded by more recent WMAP. There was this intriguing paper about 6 months ago by Hirata van Wandelt at the University of Illinois, claiming to have found a positive FNL in WMAP. I'm really at a loss to tell you what you should make of this. On the one hand, I haven't been able to identify anything that they did wrong, and neither has anyone else, that would explain that. On the other hand, it's quite surprising. Maybe some of it is just a statistical fluctuation. Maybe some of it is real. Time will tell. And then just a few months ago, the WMAP 5-year analysis appeared. This analysis comes up with a value of FNL that's just under 2 sigma away from 0. This is of course consistent with Gaussian. I've written 2 sigma error bars here, I'm waiting to see what other groups do with this data set, including Hirata van Wandelt, and also Kendrick Smith, I'm told, is working on this problem. So I expect we will hear more soon on the CMB side of things. On the large-scale structure side of things, I mentioned this paper by Neil Dalal and company that very nicely showed in both Press-Schechter type calculations and also within body simulation that you would get in an FNL type cosmology, you would get a scale-dependent bias. And I'll go through the derivation a little bit. I'll go through our version of the derivation. And then there have been a number of papers more recently that have explored this with alternate derivations, determining what are the essential pieces of physics that go into this result. And I will talk about the work that Andrzej Sosa or Rochelle and I did, where we tried looking at this in actual data. And there are more papers on this appearing, it seems, every week now. So pretty soon I'll be able to give the talk, and it will just be page after page of papers. So what's going on here? How can you measure FNL with large scale with power spectrum of large scale structure? So I think the way to think about this is in the context of these peak background or long wavelength, short wavelength splits of the density field. So if I do this to the potential field in a Gaussian cosmology, I can take phi. I can write it as phi long wavelengths and short wavelengths. And those are independent because in a Gaussian case, each k mode is independent, and the long and short wavelength modes don't talk to each other. And so then I can write the density just by taking the Laplacian of this and putting in a transfer function. And the density, because this is all linear transformations, is determined by long and short wavelength modes, and those are independent. And then all of the things you learn in textbooks about how the local density of galaxies should only be proportional to the local value of delta L plus the random component, because the delta L is basically just modulating the baseline of delta, and you need some critical threshold for collapse or whatever. All of that goes through very nicely. In the non-Gaussian case, that's not true anymore. And the reason is that if I take this phi, and I do this F and L type remapping to it to get the actual potential capital phi, and I look at the long and short wavelength components of that, the long wavelength components, so you just get basically what you'd expect. But the short wavelength components have this piece that involves, because I'm taking the square of the potential, I have these pieces that involve the product of the long and short wavelength components. So these, algebraically, these three terms are just F and L times phi squared. But what's important is that these are short wavelength, even if these are not, but they do involve the large-scale field. And then I've written this alpha here, which is just some type of convolution operator, something that takes the potentials and multiplies them by k squared and a transfer function. So the bottom line that you can see here is that the short wavelength density perturbations, so this is going to basically be a Laplacian, and it's not going to act on something that has only long wavelength modes. So this short wavelength density field actually has an amplitude that is modulated by the large scale potential. And this fact is the basis for the rest of the talk. So, so as I said, the amplitude of the small scale perturbations is modulated by this factor involving the large scale potential. And so you can think of that as basically a modulation of sigma 8. The shape of the power spectrum is not changing, at least as long as we don't have any weird scale dependences in F and L. But the amplitude sigma 8 varies from one region to another. So if I imagine setting up an in-body simulation in F and L types of initial conditions, I've got a giant box, and I've got one value of sigma 8 over here, and a different value over here, and a different value over here. And this is going to give me long wavelength perturbations in the galaxy density on top of what I would normally have. As an aside, I should comment that if I look at really, really large scales, if I were able to look outside the horizon, which of course I can't, then this modulation of sigma 8 would continue. And for a truly scale invariant power spectrum, I would find that the universe on very large scales is actually very, very inhomogeneous in an F and L type model. But I can't observe any of that. What I can observe is that this modulation gives me an additional contribution to the bias. So bias is galaxy over density versus matter over density. So this non-Gaussian bias is the usual contribution plus I better add in this term. So there's 2F and L. Alpha was the transformation from potential to density. So this is like a d potential d density. And this is a derivative of the number density with respect to log sigma 8. So this whole thing is just derivative of log number of galaxies divided by delta. And these other factors I can actually evaluate. And the end result is that the bias of the galaxies, in addition to having the usual term that I would have in a Gaussian cosmology, has this piece, which has an interesting k dependence. It becomes very large if k is very small, times this additional bias parameter. This thing that tells me how the number density of galaxies changes when I change sigma 8. So if I'm going to use this to measure F and L, I'd better know something about that. So let's talk about that. If you believe in a universal halo mass function, which, at least at a very basic level, appears to work in simulations, you can argue about how good it is in detail. But what this would give you is this derivative, how much the number of galaxies changes when I change sigma 8, is the critical density for collapse, which is about 1.7, and then there's a bias minus 1. So what this is saying is that very, very massive halos, for example, have a very high bias, and so this derivative is also very large. If I make a small change in sigma 8, it makes a huge change in the number of high mass halos. If I go to very, very low mass halos, so the bias is less than 1, then this is actually negative. So cranking up sigma 8 means that all of those guys have gotten merged into eaten. And of course, in between, if I look at dark matter particles, dark matter particles have bias 1, and so you get 0 here. That's a good thing. The number of dark matter particles should not depend on sigma 8. So if you're going to use this to constrain F and L, you want to use a tracer of large-scale structure which has a large bias. You'd like B to be quite a bit greater than 1, so that you are sensitive to F and L, because this multiplies F and L. So if that's 0, then I'm in trouble. Just as a warning about this, everything I said back there was about halos, but what you actually observe is not dark matter halos. You observe galaxies, quasars, some type of object that is luminous, and it's not entirely clear that, in fact, there are cases where there are good reasons to believe that these objects may not democratically populate all halos of a given mass M. So an example which is relevant here is quasars, where you could imagine that they form only in recently merged halos. That's an extreme case. Even if they form when galaxies merge, that's not the same thing as halos merging, but one has to be mindful of these issues. So if I do this with, for example, quasars, and I go back to my formula for the bias, then this formula gets modified from the usual relation 2 ways. One is that the relation between the standard Gaussian bias and the mass may be different. That's called assembly bias. It's been studied in a number of papers in the past 3 or 4 years. And the other is that this quantity here may be different from the quantity for all halos of mass M. So there are those two changes. The extended Press-Schechter formalism at least gives you a prediction for what this should be. It tells you, it actually does not give you an assembly bias, which is one of the problems with extended Press-Schechter. But it does tell you that the probability of a halo being a recent merger is proportional to 1 over sigma 8. And if you take those two things, then you get an extended Press-Schechter prediction for how the number density of recent mergers should vary with sigma 8. And it's very similar to the formula for galaxies, except that there's this minus 1 that comes from that exponent. Now you can ask how good this is. Extended Press-Schechter often does not do very well, depending on the particular quantity that you're asking it for. So how well does it do on this? So this particular scaling with sigma 8, if you actually look at in-body simulation, appears to work rather well. In the matter-dominated regime, changing sigma 8 is the same as changing redshift. So you can go to, for example, these guys at Berkeley, who who measured merger trees in the Millennium simulation, and you find that this exponent is good to about 10%. Is there a reason why extended Pressure is doing that well? Is there some fundamental reason why it should get this right? Or is it just an accident? I don't know. But the bottom line is that if you're counting recent mergers, this formula is probably at least a reasonable place to start.
So recent means like what? I mean, what exactly?
So in extended Pressure, this scaling law does not depend on what you assume about the time after the merger, as long as it's short compared to a Hubble time. And it does not depend on the progenitor mass ratio, as long as you take the same mass ratio.
So for very, very massive, like clusters, for example.
Yes. It depends in some complicated way on halo mass. But it does not, in extended Pressure, it does not depend on anything else. These guys actually have some interesting plots of merger rates compared to extended Pressure, and it's amazing how this works, even though almost nothing else about extended Pressure does. It's something for you to explain. So applying this to the Sloan Digital Sky Survey, so what we used in the work with Andrzej Slosar, we basically had we had a number of large-scale structure samples. The ones that were most important were the spectroscopic LRGs that Max Teckmark and company played with, or at least in the power spectrum for, and made really beautiful plots. We used the photometric LRG sample from Nikhil Padmanabhan. We used Shirley Ho's sample of photometric quasars, and this is, we used a particular redshift range. This was selected based on the, on looking for basically when the quasar photoz's are good. This corresponds, I think, to putting magnesium 2 in the R band or something like that. There's another slice which we ended up excluding because it correlates with the stars at 3 sigma, which is not a good sign if you're doing large-scale structure. And we also use the ISW cross correlations that Shirley Ho measured, but it's not actually adding anything, at least at the present time. There are too many degeneracies. Especially since one of the samples used for ISW, that would be the NVSS radio sources, has an almost unconstrained redshift distribution once you allow for all these strange bias effects. We added the microwave background and supernova data with the theory being that in order to measure scale-dependent bias, you actually need to know the shape of the underlying matter power spectrum. And since you're looking at a model where you can't use galaxies to do that, you actually need to incorporate both the CMB to tell you the shape and the supernovae to tell you what scale that corresponds to today. You can't use the BAOs because those are already included here and you don't want to double count the constraint. So you look for the excess power that you would get from bias having this 1/k² piece in it. So just to show you what this looks like for the LRGs, and I showed this for f and L equals -100, 0, and +100. This is a plot from the Slosar et al. Paper. So here's the power spectrum. There are the data points. As you can see, there's not a detection here. If you sort of squint at this in the linear regime, you might imagine that you see something a little bit positive. It's only 1 sigma. So this is perfectly consistent with Gaussianity. And for reference later in the talk, I'll just mention that the fluctuations you're looking at the largest scales are of the order of 10%. The quasars are a little bit uglier. So here, you're actually going to much larger scales because these quasars are redshift 1 point something. So in the case of positive FNL, you're seeing at very small L, this huge increase in the power, if you look at the theory curve. In the case of negative FNL, the bias actually goes through 0 and becomes negative. And that's because the overdense regions of higher potential, in this case, actually have smaller sigma 8. So you can actually get negative bias out of this. And if you look at the first couple of data points, they really don't like FNL equals 100. And that's actually where our main constraint is coming from. But this is a hard measurement. These theory curves go up to 1.7% in LL plus 1 over 2 pi. It's basically coming from this formula, the potential variation times FNL and such. So that's where we are, and doing much better than this is going to be a huge systematics challenge. So here are the constraints on FNL. The quasars, we tried a few different versions of the analysis using the merger bias formula, using a couple of different forms for the likelihood function, because you worry at the lowest L's that the likelihood function could be strongly non-Gaussian. And then the bottom one, we've combined all of these things together and also with the CMB. So here's what one gets. So I put the WMAP5 number up here. The large-scale structure error bar that Andrzej got from his Markov chains is here. And you'll notice it's highly asymmetric because of the complicated dependence of the power spectrum on FNL. Basically, the excess power in the quasars is cutting off the high tail of this error distribution. And then you can combine them, which is what we always do in cosmology. And you get an amazingly tight constraint on FNL. It's less than 70. There's approximately 2 sigma evidence for FNL positive. What is that? I think it's a statistical fluctuation. Certainly one should not get too excited about 2 sigma. You could wonder if it's systematics. The CMB measurement is what's pulling you up, so you might imagine it's foregrounds, although nobody's come up with a foreground that does this. The simple estimates are quite a bit less than that, so I think that's unlikely. The spectroscopic LRGs are the data set in the large-scale structure that pulls this up by about a sigma. But getting 10% excess power, that seems a little bit far-fetched, given how well the survey seems to be calibrated and how many things work at the couple of percent level. So I really think it's this. I'd be excited if it's the next big thing, but really it's 2 sigma, and so only one person I've talked to really thinks this, and he's a theorist. So where are we going? So the Planck satellite will make the error bars from CMB a factor of several smaller than WMAP. If you can control the foregrounds and the systematics, I'm actually optimistic about these, because if you look at the simple estimates of those, for example, that Dan Babbage and others have been playing with, that may actually be doable. What I'd like to focus on is the large-scale structure technique. And I've shown you constraints with both photometric and spectroscopic samples. We'll have a lot more of these over the coming years. These from the weak lensing surveys, painting the sky with photometry, and these from baryon oscillation surveys. So we'll get a lot more data, but there are problems. A minor one is that you have to calibrate your FNL estimator. You need to know d log n d log sigma 8. I don't think this is a huge problem because you only need approximate knowledge of that unless you have a mini sigma detection, which is where I wish we were, but we're not. A bigger one is photometric calibration. I was showing you a quasar power spectrum where that first data point was 1% fluctuation in the quasar density. And that was very, very hard to accomplish, and it required the work of a large number of people on Sloan to make something like that possible, one of whom is staring at his computer right now instead of listening to the talk. finally, there's galactic extinction. And as you push below the percent level and look at large angular scales, this is a big deal. And I'd like to point out that getting to FNL of order 10 instead of 100 means we have to get these systematics down to 10 to the minus 3, which is an order of magnitude better than we're doing today, and I think much better than any type of large-scale calibration has ever been done in any waveband to my knowledge. So, ouch. So in my last 2-3 minutes, I will tell you that all is not lost. So I think by the usual way of trying to understand from first principles and studies of galactic objects and such, trying to get to 10 to the minus 3 is very, very hard. The atmosphere doesn't behave. Your optics and your filter transmission do not behave at this level. If you go to space, you get rid of this problem, but space does not guarantee stability. The dust maps are a mess, even at levels above this. You have finite bandpass width, so getting to 10 to the minus 3 calibration may not be possible in software if you have fluctuations in your effective bandpass. So all of these things, I think, make it very hard to do this in sort of a let's just control our systematics this well and not worry about it way. On the other hand, FNL doesn't look like systematics, or at least it doesn't look like the usual systematics. So what does it do? It's bias dependent. So calibration errors don't change your number of objects. They don't change phi star. They change L star. So you might imagine that, whereas FNL, or a variation in sigma 8, changes both. So you might imagine that by trying to measure all of these things, by using the full luminosity function in each portion of your volume, you might be able to make some gains. Of course, you lose in statistical power by doing that, so we can't do it with the Sloan quasars. But with some of these upcoming mega surveys, maybe. If you cross-correlate two different surveys, most of these problems go away. The dust extinction is the exception. Maybe you go to the radio where there's no dust extinction. If you're stuck in optical or IR, you could use the redshift dependence. If I miscalibrate one of my band passes, it tells that actually should produce a particular redshift dependence. So if I see a particular mode in redshift that varies on large angular scales, in particular if it's aligned with my survey strategy, that's a red flag. So I could try to project out those modes. If my extinction law is incorrect, that again gives me a specific set of modes. If it's spatially variable, which at some level it must be, then you worry about other things. There are lots of galaxy diagnostics that you could use, but you worry that if you change sigma 8 in one region due to this FNL type effect, that those diagnostics will also change. So if you see that, how do you know it's not actually FNL? I think there's a lot of work to do there by whoever's proposing the next generation surveys. Another thing is that this effect, at least if it's truly FNL, correlates with the density field. So it's an effective change in the bias. So if I go to really large scales, where, for example, the standard, if I look at a scale where the standard Gaussian galaxy fluctuation would be 0.4%, and FNL is giving me 1%, those add in phase. So the total is 0.5%, and that, in order to mimic that, you actually need 0.3% in uncorrelated systematics. So maybe by using that, essentially using the shape of the power spectrum, one can separate this type of systematic from FNL, or at least focusing on the right region in K-space, you may be able to do better. And finally, if you're going to do this, you need to go to somewhat higher K than a Hubble length. You want to go to a K that's of order, I guess, a few times the square root of FNL times H naught. It may be that this is a case where you want to do it with spectroscopic redshifts rather than a photometric survey. So to summarize, right now the large-scale structure measurements are competitive with the CMB. We don't have a detection. Combining everything, including the CMB, we're at 2 sigma. And as I said, very few people would get too excited about that. Large-scale structure, if I get enough galaxies, statistically could get to FNL with a few, but the systematics are hard. So I've told you what you need to do. You need somebody to very carefully engineer out as many of your systematics as possible, and you need data people to clean up what's left. You need enough statistical power to do the types of systematics projections that I was talking about. So what do you need for that? What does this imply for a survey? You need large area depth, lots of band passes, and as many spectra as you can get. Finally, it's too early to say how hard this is, how many of these things you actually need, and how well we will ultimately do with this type of technique.
Time for a few questions. Gary.
Is there a lensing signature of this? If you correlated the potential fluctuations that you see from lensing, we measure sigma 8 from lensing, right? That's our primary variable. So is there some obvious 3-point or 2-point statistic you would use?
So in the in the case of the lensing, I can think of two things. So I guess in principle, because you're directly measuring matter, if you understood the baryonic effects, you could actually use the lensing bispectrum. I'm not sure if that's viable. I guess the other thing regarding this large-scale stuff is you could, in principle, do a cross-correlation between the galaxies and the shear. And that would, because the shear is sensitive to a completely different set of systematics, you might imagine that would solve some of your problems. On the other hand, if one is doing this with galaxy samples at redshift 1, and you actually look at the shear power spectrum at L equals a few, it's the range of angular scales we're talking about, even if I put my sources really far away, most of that power is coming from nearby because of the power spectrum. So I'm not sure how much overlap you could actually get in terms of the window functions. I suppose with some type of nulling tomography you may be able to do that, but then your spurious power on very large angular scales had better be very good.
Okay, Francis?
Just to comment about the last question, yes, very fast. But I'm a bit surprised not to see a lot of reports in bias, the k-dependence of bias, and not so much bias spectrum focus. So FNF is directly something that's related to bias spectrum. And so about lensing, I guess what we look for is modulation of sigma 8, the region of the sky, and but you have a tracer of the density of this region. So it may not be regions that. So it's a modulation effect basically with star. This kind of.
So you're saying take several spots on the sky and say what is sigma 8 in this spot here, here, here.
And if I have long wavelengths that correlate with these wavelengths, I have a signal of FNF.
That is correct. I think that would work.
That's practically what CMB people are doing. It's correlating low L with small L fluctuation of the amplitude of signal.
Right.
But this is just well, and I guess a way I'm not sure now if CMB is going to be better than classical Oscar structure constraint of FNF. By the way, this is a very old idea that non-Gaussianity rise from clustering is in competition with bound of non-Gaussianity. What's new is a formulation in terms of a specific k-dependence as we wrote it this way.
That's correct.
And since you are trying to fit k-dependence within this clustering invariance region, there should be a very simple, ultimate precision with which you can measure that.
Well, if you have multiple density tracers, and they're tracing the same underlying density field, but with different biases, then in principle, I'm not saying this is practical, but in principle, you would be limited by the Poisson noise of those tracers, even on the large scales where you have only a few modes.
Touch the mouse, can you?
Okay, so the thing is not very specific variance limitation, but Poisson noise limitation.
That's correct. And there may be a correlated Poisson noise limitation in the sense of one halo Poisson noise, but it's not as bad as saying you have 10 very large scale modes, therefore you cannot measure to better than 1/√10.
Any other question? No, if not, let's thank Chris again.